Namaste dosto. Imagine you're about to watch a thrilling cricket match and you want to know the chance your favorite team will win. But wait, what if you already know they won the toss? How does that change things? This idea of updating chances based on new info is what we call conditional probability. So, what exactly is conditional probability? Simply put, it measures the likelihood of an event, say event A, happening given that another event B has already occurred. We write this as P of a given B, or symbolically P of a vertical bar B. Mathematically, conditional probability is defined as P of a given B equals P of a intersection B divided by P of B. And here's the important part, P of B must be greater than 0, because we are considering the world where B has happened. Let's pause and repeat that slowly. P of a given B equals P of A intersect B over P of B. You can think of this as focusing on a smaller, reduced sample space where the event B is true. For example, if B is, it rained today, then we only consider outcomes where it rained when calculating the chance of A. This updated view helps us incorporate new information or constraints into our probability predictions. Imagine a Venn diagram with two circles overlapping, one for event A, one for event B. The overlapping part, A intersection B, represents the scenarios where both happen. Conditional probability zooms into the B circle and looks only at that overlap to find how likely A is, knowing B has occurred. So that's our introduction to conditional probability, the perfect tool for reasoning under updated conditions. Ready to explore its key properties next? Let's smoothly move on to the main properties of conditional probability. Think of it like this. Whenever we work with probabilities, they always stay between 0 and 1. Conditional probability keeps this rule intact. So, P of a given B is always greater than or equal to 0 and less than or equal to 1. Simple but very important. Now, what if we have two mutually exclusive events, say A and C, that cannot happen together? If we know that B happened, then the chance of either A or C happening given B is just the sum of their individual chances given B. In formula terms, P of a union C given B equals P of a given B plus P of C given B. Another interesting case is when events A and B are independent. If knowing that B happened doesn't change the chance of A, then P of a given B equals simply P of A, the original probability. Independence means no influence between events. Picture a Venn diagram with three circles, A, C, and B, with A and C not overlapping. This helps us see how their combined probabilities behave within the B circle as our conditioning event. These properties give conditional probability its logical backbone, letting us calculate new chances confidently whether events overlap or stand apart. How about a quick pause here before we dive into how we multiply probabilities for combined events? Now that we understand conditional probability, let's explore the multiplication theorem, also known as the chain rule of probability. This theorem connects conditional and joint probabilities in a very neat way. Suppose we have two events A and B with P of B greater than 0. Then, the probability that both A and B happen together, that's P of A intersection B, equals P of B multiplied by P of a given B. In words, the chance of B happening times the chance of a happening given B. If we rearrange this, we get back the familiar formula for conditional probability. P of a given B equals P of A intersection B divided by P of B. So, multiplication and conditional probability are two sides of the same coin. This concept extends beyond two events too. For example, with three events A, B, and C, the probability that all three happen together is P of A multiplied by P of B given A, and then multiplied by P of C given both A and B. This is written as P of A intersection B intersection C equals P of A times P of B given A times P of C given A intersection B. This theorem is especially useful in multi-step experiments or situations where events depend on each other, like drawing cards one after another or outcomes in a probability tree. Imagine a tree diagram splitting off branches. Each branch shows conditional chances depending on earlier events. This visual helps us stay organized when dealing with complex, layered probabilities. Before we move to some solid examples, Let's take a quick mental break to see how multiplication theorem links joint and conditional probabilities. Alright, let's put theory into practice. Imagine throwing a single six-sided die. Our goal is to find the probability that the outcome is even, given that the roll is greater than 3. How do we tackle this? First, our sample space S is the numbers 1 through 6. 1, 2, 3, 4, 5, 6. Define event A as roll is even, so A is 2, 4, and 6. Event B is roll is greater than 3, so B is 4, 5, and 6. The intersection A intersection B is where both events happen, 4 and 6. Next, calculate P of B, which is the number of outcomes in B over the total outcomes, 3 over 6 or 1/2. Then, P of an intersection B is 2 outcomes over 6 total outcomes or 1/3. Finally, by the conditional probability formula, P of a given B equals P of a intersection B divided by P of B, that is 1/3 divided by 1/2. Doing the math, 1/3 divided by 1/2 equals 2/3. So, the chance of rolling an even number, given that the roll is greater than 3, is 2/3. Arey wah! This simple example clearly shows how conditional probability focuses our attention on a smaller, relevant subset of outcomes. Picture a diagram mapping the 6 outcomes, highlighting those in A, B, and their overlap, helping us visually see our calculation. Ready to try a card example next? Now let's bring in cards to the game. Suppose you draw 2 cards one after the other from a full deck of 52 cards without putting the first card back. What's the chance that the second card is a king, given that the first card drawn was also a king? Initially, the chance the first card is a king is 4 kings out of 52 cards, so 4 over 52. Once that king is drawn and kept out, only 3 kings remain in the remaining 51 cards. So, the probability that the second card is a king given that the first was a king is 3 out of 51. Mathematically, P of second is king given first is king equals 3 over 51, which reduces to 1 over 17. This follows the conditional probability principle exactly. The sample space reduces after the first draw, and the probability for the second event updates accordingly. Imagine a tree diagram branching from the first draw, king or not king, and then showing probabilities for the second draw key to each branch. This helps us think clearly about dependent events and changing chances. Isn't it amazing how conditional probability helps navigate such real-world problems like card games? Let's now explore how to distinguish independent from dependent events. Here's a crucial pair of concepts: independent versus dependent events. When 2 events A and B are independent, knowing B has occurred doesn't change the probability of A. Formally, P of a given B equals P of A. And this works both ways. However, if events are dependent, the occurrence of B influences the chance of A. Here, P of a given B is not equal to P of A, clear evidence of dependence. Another way to check independence is by its multiplication rule. P of A intersection B equals P of A times P of B. If that holds true, the events are independent. Picture 2 circles. In one, A and B overlap, meaning the events are dependent. And in the other, A and B are separate without overlap, indicating independence. Visuals like these make the abstract idea stick. Let's unlock the total probability theorem, a fantastic tool used in layered probability problems. Imagine events B1, B2, up to Bn are mutually exclusive and cover all possible outcomes, what we call exhaustive. Then, the probability of event A can be broken down as the sum over all I of P of B sub I times P of a given B sub I. In simple words, P of A equals the sum of the probabilities of each B event multiplied by the probability of A occurring given that B event. This theorem lets us express a complex probability as a weighted average of conditional probabilities over different scenarios or partitions of the sample space. That's especially handy in decision trees or experiments with many layers. For example, which route a train may take next, or whether a machine produces a defective item under different conditions. Picture a tree diagram branching out through all BIs to event A, illustrating how each path contributes to the total probability of A. Wonderful. Now you're ready for an applied example involving defective bulbs from a factory. Here's a real-life application. A factory has 3 machines, A, B, and C, producing 25%, 35%, and 40% of the total items respectively. Each machine has its own defect rate, 5% for A, 4% for B, and 2% for C. We want to find the probability that a randomly selected item is defective. Define event D as defective. Using the total probability theorem, P of D equals P of A times P of defective given A, plus P of B times P of defective given B, plus P of C times P of defective given C, plugging in numbers. P of D equals 0.25 times 0.05 plus 0.35 times 0.04 plus 0.40 times 0.02. Doing the math, 0.25 times 0.05 is 0.0125, 0.35 times 0.04 is 0.014, and 0.40 times 0.02 is 0.008. Adding them up, 0.0125 plus 0.014 plus 0.008 equals 0.0345. So the overall chance of picking a defective item is 0.0345 or 3.45%. Arey wah! That's how theory helps solve practical problems perfectly. Great work. Now let's wrap up our journey with a quick recap and some key takeaways. Time to tie together everything about conditional probability. First, remember the key formula 1. P of a given B equals P of A intersect B divided by P of B, where P of B is greater than 0. Then, formula 2 shows the multiplication link. P of A intersect B equals P of B times P of a given B. And finally, formula 3, the total probability. P of A equals the sum over I of P of B sub I times P of a given B sub I for mutually exclusive, exhaustive B sub I events. The big idea is that conditional probability works on a smaller world where the given event has happened, letting us update probabilities with fresh information or constraints. It's especially useful for dependent events, multi-step predictions, and forms the foundation for advanced concepts like Bayes' theorem, independence, and total probability. Keep practicing these formulas and examples. Mastery here not only helps in your exams but sharpens your logical thinking for real-world uncertainty. Excellent beta. Remember, conditional probability is like solving a mystery with clues, updating your guesses as more facts come in. Keep solving those puzzles. Science and maths will become your best friends. Shabash. Keep practicing and stay curious.